Hello everyone, and welcome to the 31st talk in the invited seminar series of the Complex Systems and Dynamics group of IIT Madras. Today, we have with us Professor Arnaud Dragicevic from Chulalongkorn University of Thailand, where he is a visiting professor in economics. He holds a PhD from Ecole Polytechnique and an SCD from Aix-Marseille School of Economics. He works on bioeconomics, sociological systems, sustainability, and also applications of graph theory and game theory to these problems. So today, Professor Arnaud is going to talk about weighted socio-ecological multiplex systems. And okay, so we can begin. Professor, the stage is yours.
Thank you very much. I would like to thank Professor Gupta for the invitation, as well as IIT Madras. So the presentation is entitled Weighted Socio-Ecological Multiplex Systems. Now, sustainability is a crucial issue that affects not only current generations, but also the future ones. Achieving sustainable development requires balancing economic growth, social equity, and environmental protection. Following the release of the well-known Brundtland Commission report, the idea of sustainability gained popularity. The most popular and often used illustration of sustainability is the sustainability Venn diagram, which has three overlapping categories: economy, society, and the environment. And it involves pursuing economic growth, social justice, and environmental quality all at once. Additionally, the Venn diagram can be used to map out different policy options. For example, it has been underlined that also the visual perspective aims to equalize the importance of the three pillars of sustainability. The model implicitly favors weak sustainable paths through economic processes. Now, specifically, weak sustainability focuses on, at the very least, preserving the overall capital stock, at best increasing it. And it contends that manufactured, human, and social forms of capital can more or less replace natural capital in both its source and sink roles. Additionally, there are no discernible variations between them in the types of well-being they offer. So as a result, any environmental degradation can be traded for using alternate kinds of capital. Now, researchers have created and supported alternative conceptual frameworks, such as the polycentric socio-ecological systems, that demonstrate how people and their environment are interrelated. Now, according to the observers, these polycentric models more accurately capture the dynamics of interactions between human societies and their environment. Now, because these coupled systems may effectively link scales via a variety of information flow capacities, polycentric systems are better suited to capture socio-ecological phenomena. A typical SES is made up of anthropogenic and natural components that interact on various organizational, geographical, and temporal scales. It is composed of nodes, and those nodes can be natural elements, resource consumers, civic participants, voters, economic actors, or regulatory agencies. The linkages between the nodes can be financial transactions or other transfers of resources like energy, information, and strategies. Now, the complexity of sustainability has led researchers to focus on specific aspects of sustainability, such as economic growth or the environmental protection. However, to truly understand the interplay between these factors, it is necessary to look at them as interconnected systems. A network consists of nodes, which stand in for the relevant entities, and of edges, which reflect their interactions. Even though networks enable us to examine a wide range of systems, including the socio-ecological ones, their theoretical underpinnings do not take into account interconnected systems like the networks of networks. And if not communicate in many ways, it would be necessary to build a layered network or a multiplex network where each layer corresponds to a particular kind of connection. Then the linkages of various types make up the network series. Now, the complexity of multi-layer networks is great because it allows one to distinguish between and model in intra-layer and inter-layer connectivities. This has become a hot issue in network theory because of its patent methodology. And now in the following study, we propose a formal model of sustainability that considers the multi-layered networks of economic growth, social equity, and environmental protection. By analyzing these networks and their interactions, our model aims to provide insights into the dynamics of sustainable development and the potential pathways to achieve it. Now, resilience has been an important concept in the analysis of SCS sustainability. In general, as you know, a system is considered to be robust when in presence of perturbations, it continues to function without fundamental changes to the original configuration. Conversely, it is considered to be resilient when it succeeds in adapting to perturbations while continuing to function, be it at the expense of some changes in its configuration. The legal structure must be then changed in order to accommodate the SCS dynamic processes in a manner that allows for resilience. So we explored the possibility of reform on multi-layered networks and the efficiency of spread of change in such systems should their actual mode of being considered to be obsolete. So utilizing the susceptible, infected susceptible paradigm, we have previously used the SCS network to study the spread of a global reform. And in this model, we had a fully working, unreacted coupling between the economy, society, and the environment. In that paper, we found that as a direct and indirect result of full-scale reform process that spreads over time through network connectedness, we exposed the SCS to the dynamics of reform through the knock-on effect. Now, what do we do in the following paper? Well, we examine how well policy changes can spread through multi-layered networks of socio-ecological systems. And for that, we are using new ideas in network science, like the Hubs attracting or Hubs repelling Laplacian, to study how changes can be passed from one part of the network to another. We are also examining how different parts of the network work together and how changes can affect the whole system. Our model considers how changes can spread through different layers of a network using a normalized Laplacian matrix. And we find that a dense network is important for changes to become widespread, and that it is best when the most important parts of the network are leading the chain. We also proved that sustainability may be best achieved when the central nodes happen to be the greatest propagators of an essential reform. Our results also suggest that it is important for all the layers of the network to work together, and then this will lead to the best outcome for sustainability. So we will now talk about the model. We have a population of agents that is distributed among Allen layers with n going from 1 to 3. We have the economic layer, the social layer, and the environmental layer. Now, each layer contains capital N nodes with I going from 1 to capital N with different intralayer connectivity. The vector of the adjacency matrices of the N layers defines this multiplex system in full. So let AN for N going from 1 to 3 be the adjacency matrix of Ln with non-negative elements Aijn. Now we consider two nodes to be connected if Aij is equal to 1, otherwise equal to 0. Each node in Ln is connected to its counterparts in L all layers of N but to 1 at stake, such that the identical nodes of various levels have a one-to-one connectivity pattern. We then construct the weighted adjacency matrix. So let Bn be the weighted adjacency matrix of Ln with non-negative elements Bijn, such that Bn is equal to the ratio between Din and Djn, raised up to the power gamma times An, where Din is equal to the sum of Aijn for j going from 1 to capital N. Now, for gamma equal to 0, it is obvious that the network remains unaltered, for En is equal to An. Whenever gamma is equal to +1 or -1, the unweighted network becomes a weighted directed network where the weights of any two nodes are represented by the ratio of the degrees of the two adjoining nodes. Now, in order to get the matrix representation of the multiplex network, we now introduce the Laplacian matrices from the weighted adjacency matrices. So the Laplacian matrix is usually defined to be the difference between the degree matrix and the adjacency matrix. We employ the normalized sinus Laplacian instead. In that case, the difference becomes the sum, and the matrix is normalized. The sinus Laplacian eigenvalues for a connected graph are non-negative, and to normalize a matrix means to scale the values such that the range is between 0 and 1. This enables us to replace the adjacency matrix by the Laplacian matrix while creating the probability measure. And the value of Lij approaching 0 implies that the intensity of interactions of the connected graph is high. As Lij tends to 1, the intensity of interactions in the nodes gets weaker. So the following figure represents a multiplex network, which is composed of the economic, social, and environmental layers. Each of them is composed of 9 connected nodes. As you might see, there's a one-to-one connection between the layers, and there's a different intra-layer connectivity across the layers. Now, agents can be either target nodes or reformed nodes, which have previously been targets. A target node must be sufficiently open for reform in order to be reformed. Now, if a target node from Ln is connected to at least one intralayer reform node, let beta comprised between 0 and 1 be the probability of openness for reform on layer N. Should the reform be called into question, let mu comprised between 0 and 1 be the risk that a reform node from Ln gets abrogated, such that it returns back to its original state. Now, given the multiplex network interlayer connectivity, let Kn such that the sum of Kn, where n goes from 1 to 3 equals 1, be the parameter of influence emanating from either layer. For instance, the weighted probability that a target node from Ln is open for reform issued by either layers is 1 minus Kn times beta n. And this happens whenever a reform arises from the counterparts in other layers. The probability that a node I from Ln gets reformed at time t is represented by T, when its complement represents the likelihood that I stays a target node. Now we first analyze intralayer connection, and we begin with a single layer before going to the multiplex networks. So we consider the normalized sinus Laplacian matrix for an isolated network. Now the evolution of P for node I from Ln is formalized by using the microscopic Markov chain approach method as the following dynamic equation 1. So in this equation, you can see that it depends on Q, and Q represents the probability that node I, despite being reform-minded, does not get reformed by neighbor J. Now, in this way, the network effect on a layer is embedded in the probability of reform failure. As you can see, the composite probability that an open node I is reformed by at least one neighbor, and the composite probability that a reformed node I is not prone to abrogation, make up the discrete dynamics. This equation helps us to emphasize the fact that the difference between the probability of reform failure and abrogation at time t determines the level of P time step t plus 1. Now, following the technique used in a previous paper, solving the dynamical equation reduces to solving the non-homogeneous recurrence relation P, from which we obtain the stationarity expression as follows: P star. The probability dynamics enables us to study the asymptotic density of reform nodes in a network exclusively dependent on intraconnectivity. So after this transient response, the average density of reform nodes is computed as follows, which is represented by rho at time t, where Q is still defined as earlier. Now, this represents, as I said, the density of reform nodes. So we observe that rho is equal to 0 whenever Q is between 1 and U. This implies that the asymptotic density of reform nodes is at its minimum given certainty that node I has not been reformed by any neighbor from Ln at time t, or when its probability of not being reformed is equal to that of being abrogated. We can now look at several scenarios. The first one is that when Q is equal 1, beta is equal to the expression number 4. Now, while L times P equal to 1 divided by beta n represents the eigenvalue of the Laplacian matrix, the reversed expression, that is beta n, equal to 1 divided by L times P, corresponds to the spillover cutoff for the active policy. And the fact that the spillover depends on the entries of the normalized sinus Laplacian matrix makes it dependent on the intensity of link between I and J, which is the inverse of the node's degree. Now, when the graph is neutral or gamma is equal to 0, the explanation is that the probability for a target node of being reformed is not high enough. In that case, the policy knock-on effect shall be considered as sterile for the threshold attains an infinity level. Should gamma be equal to 1, such that the topology is Hubs repelling, or gamma equals to -1, such that the topology is considered to be Hubs attracting, the interpretation is different. So when gamma is equal to 1, this means that small degree nodes produce a large influence on high degree nodes. And this means that the intensity of interaction between the nodes is high, which normally enables the reform to spread easily. Despite such a configuration, The repulsive interaction, illustrated by the inability of central nodes to influence their connections, prevents the reform spreading from taking place. When gamma is equal to -1, high degree nodes produce a great influence on small degree nodes. And given the low intensity of interaction between the nodes in that case, we are in presence of a weak attraction that fails to trigger the reform. Now, the second equality, or the expression number 5, when Q is equal to mu, we obtain the following ratio for beta. Now, this time the spillover threshold amounts to 1 minus mu n raised to the power 1 divided by n, the whole being divided by L times P. When the graph is neutral or gamma is equal to 0, this expression tends to infinity as P tends to 0. And this expression tends to 1 minus mu n raised to the power 1 divided by n when P tends to 1. Now, in the first case, as the probability of reforming node I by neighbor j at time t goes to 0, the spillover threshold goes to the unattainable level of infinity, which yields a 0 density of reform nodes. In the second case, the spillover threshold is equal to 1 minus mu n raised to the power 1 divided by n, which is 0 for large values of n. So we fall on the same property in both cases. Now, when the graph is weighted, which means that gamma is equal to -1 or +1, we have the expression equal to 1 minus mu n raised to the power 1 divided by n divided by L when P equals to 1, which means that for a fixed capital N and mu equal to 0, beta shall tend to infinity with gamma equal to 1. And when gamma is equal to -1, beta will tend to 1. According to the spectral analysis, in the first instance, the Hobbes repelling topology jeopardizes the reform spread despite a positive eigenvalue. In the second case, the weak attraction between the nodes fails to expand the reform. So regardless of the fact that the smallest eigenvalue shows a connected graph, the algebraic connectivity reveals a poorly connected graph, and this confirms the fact that we are in presence of a low attraction between the nodes.
Can I interrupt for 1 minute? Which slide are you on?
Excuse me?
Which slide are you on? Number 14?
Yes, number 14, yes.
Okay. I thought I had missed a slide.
No, 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 no. I'm still explaining the expressions and what they involve. So finally, we have that when rho is strictly positive, Q is less than mu. And this implies that the asymptotic density of reformed nodes is strictly positive when the probability that node I has not been reformed by any neighbor at time t is less than that of being abrogated. So in that case, beta is comprised with those two expressions. So is strictly greater than the ratio 1 minus mu n raised to the power 1 divided by n divided by L times P, and is strictly less than 1 divided by L times P. Now, when the graph is neutral, which means the gamma is 0, we have the limit that tends to infinity. As P, or the probability to be reformed, tends to 1, we obtain the limits of 1 minus mu and 1. Now, the interval in which the spillover threshold is present tends to a reasonable level of infinity when the likelihood forming node I by neighbor j tends to 0. The spillover threshold for large values of n sits between 0 and 1 as the likelihood forming node I by neighbor j at times t approaches certainty. So as a result, achieving positive asymptotic density of reformed nodes is enabled by a significantly high likelihood of reform completion, and a weighted graph, which means that gamma is equal to 1 or -1, leads an eigenvalue which is bounded by L times P on the left side and by L times P divided by 1 minus mu on the right side. Now, as mu heads towards 0, the spillover effect is easy to trigger, because all it takes is that beta is greater than 0. Now, from the viewpoint of the spectral analysis, the Laplacian eigenvalue discloses that the reform depends on L. When L approaches 0 and the intensity of interactions is elevated, the graph simply needs to be connected. When L tends to 1 and the intensity of interactions is small, the spread of reform can only be achieved for a densely connected graph. And finally, when rho is equal to 1, which means that all the nodes have been reformed on a layer, this implies that mu is equal to 0, which means that the new probability of reform aggregation enables to strike full density of reform nodes. So this leads us to the following proposition. In a network exclusively dependent on intralayer connectivity, positive density of reform nodes on a layer, which is proportional to the probability of reform completion, depends on the levels of entries of the normalized sinus Laplacian matrix. Now, with a weak intensity of interactions between the nodes, a densely connected graph is necessary for the reform to become widespread. And the maximum asymptotic density of reform nodes simply depends on the absence of risk of reform abrogation. Now we move to the next level, where we study both intra and interlayer connectivities. So this time, the average density of reform nodes is the following expression. So it is much like the previous case, but this time, if you take a closer look at Q, you observe this K. So once again, Q is the probability that node I, despite being open for reform, does not get reformed by neighbor J, either through intra or interlayer connectivity. So in this case, Q is also dependent on K, be the effects caused by the counterparts who have undergone reformation in other layers. So a node is reformed on another layer, and this spreads to the layer at stake. Now, when the graph is neutral or gamma is equal to 0, we observe once again that rho is equal to 0, which implies that Q is between 0 and mu. Now, more specifically, when Q is equal to 1, this yields beta now dependent on 1 minus K, which means that when the probability of reforming goes to 0, the spillover threshold goes to infinity. So despite the impact of nodes from both the surroundings of node I and from the other layers, the polycentric effect will be waned. Now, if the graph is weighted, which means that gamma is equal to -1 or 1, and if the reform approaches certainty, which means that P tends to 1, the spread becomes infertile because Q tends to 0 or because L tends to 0. So this means that either the influence from other layers is not big enough, or the topology is Hubs repelling. Now, when Q is equal to mu, the threshold once again amounts to beta, which is dependent on K. And as K tends to 0, we obtain a level of beta equal to 1 minus mu up to 1 divided by n, the whole being divided by L times P. Now, this means that when the combined influence from L is not enough, the policy knock-on effect will depend on the probability that node I gets reformed by node J via K at time t. Now, as the probability of reform tends to 1, which means tends to certainty, the spillover threshold depends on L. A weighted graph, which means that gamma tends is equal to 1 or -1, shall lead to a restrained reform transmission, either because of a repulsive interaction between the nodes or because beta is equal to 0 for large values of n. And this is whenever the intensity of interactions is unelevated. Now, on the other side, Skn tends to 1, which means that the influence from other layers goes to 0. This yields another impossible high level of threshold. In any case, zero density of reform nodes will be the outcome. As rho is strictly positive, which means that you get some reform of nodes on the layer, this implies that Q is less than mu. Once again, we have beta bounded both on the left side and on the right side. Now, when we have an unweighted graph, which means that gamma is equal to 0, and when the reform tends to certainty, which means that P tends to 1, beta is between 0 and 1 for large values of n. When the likelihood of reforming node I by node j through k at time t is close to certainty, the spillover threshold lies within 0 and 1 for large values of n, which means that a positive reform on a layer can be obtained, high probability of achieving reform in other layers. So it means that you have porosity between the layers in this multiplex network. When the graph is weighted and the probability of reform tends to 1, the knock-on effect can be achieved when L tends to 0, or gamma is equal to 1, since beta needs to be less than infinity. Now, put differently, that means that the high intensity of interactions will facilitate the spread of reform. When gamma is equal to -1, which means that L tends to 1, we have beta less than 1 for k equals 0, and beta less than infinity for k equal to 1. Now, this means that when the topology is Hubs attracting and the intensity of interactions between the nodes is small, it will be easier to propagate the reform from the layer itself and from the counterparts in other layers. Now, what we can learn from the spectral analysis is that in all cases, when k tends to 0, an eigenvalue such that 1 divided by beta needs to be less than L times T, which generates positive constraints. And the question we might ask ourselves is what happens when the probability of reform is of 1? Now, in case of a densely connected network, which means that we have a weak intensity of interactions between the nodes, the knock-on effect will come from high-degree nodes present on other layers and from a high intensity of interactions within the layer should the multiplex graph be poorly connected otherwise. So this brings us to the following proposition. In an interacting multiplex network, both dependent on intra and interlayer connectivities, a positive density of reform nodes on a layer, which is proportional to the probability of reform completion, depends on both the levels of entries of the normalized sinus Laplacian matrix and the level of influence coming from the reform counterparts in other layers. Now, with a weak intensity of interactions between the nodes, a densely connected multi-layered graph is necessary for the reform to become widespread. And the maximum asymptotic effect density of reform nodes simply depends on the absence of risk of reform abrogation. Now we move on to the study of stability and synchronization. So we examine the stability of the equilibrium density by studying the explicit time discretization. And this enables us to analyze the multiplex network both in space and time. Now we observe the following property, the following inequality. We decompose the multiplex time evolution into two subspaces, namely the intralayer and interlayer spaces, such that the multiplex coupling equals delta rho, being a sum between delta rho n and delta rho all n but the one at stake, with the sum being the Kronecker sum. Now, this splitting scheme enables us to treat multi-scale spaces where one identifies fast and slow components. The fast dynamics are considered to take place inside the layer, while the slow dynamics correspond to the updates coming from other layers when the information takes the long way. And through this explicit time discretization, we can study the stability of the equilibrium density such that the reform remains in place for a time step of size delta t. Now, according to this rule, the reform dynamics relative to the multiplex network is considered to be stable if the time evolution of the density of reform nodes inside the layer is greater than or equal to the time evolution of the density of reform nodes on the other layers, weighted by the constant 1 plus delta t squared divided by 2 times alpha, where alpha is between 0 and 1. And it corresponds to a constant which balances the intra and interlayer terms. Now, this entire expression encapsulates the fact that in socio-ecological systems, intralayer interactions are stronger than interlayer interactions. So basically, what happens inside the layer is stronger than what happens between the layers. Yet, in order to achieve sustainability, sustain the multiplex network, the load gap, they cannot exceed delta t squared divided by 2 times alpha. Now, whenever this inequality 8 is a strict equality, the multiplex network is considered to be synchronized. That is, the whole system updates within a limited time lag. And this small time lag is due to the update inside the layer once a reform has reached it. Otherwise, we consider the system to be desynchronized, in which several states cohabit. This gives the following proposition. In an interacting multiplex network depending both of intra and interlayer connectivities, the equilibrium density of reform nodes reaches stability when the intra and interlayer couplings undergo a balanced load. When the time evolution is synchronized across the multiplex network, its topology is preserved. Let us now move on to the simulations. So in these figures, we see the levels of spillover thresholds for a single layer. We have capital N being equal to 100, and we have different levels of gamma going from -1 to 1. Now the x-axis corresponds to probability that node I is reformed by neighbor J at time t, while the y-axis denotes the probability mu that a reformed node from L gets abrogated. Now darker blue areas corresponds to lower level of spillover threshold, basically strictly greater than 0. Light blue areas correspond to unreachable levels of threshold such that beta tends to infinity. Now, when P tends to 0 and mu tends to 1, we see a series of decreasing convex curves with a corner equilibrium from which emerge the bell-shaped areas that delimit the values of beta and are depicted in the shades of blue. We verify the property that mu is equal to Q. So as we move from gamma equal to -1, from equal to -1 to gamma equal 1, going through gamma equal to 1, The spillover threshold values increase from a value of 4.50 to a value of 450,000. Now, the simulation results show that the higher probability of reform, the smaller the threshold constraint that enables to set off the policy reform knock-on effects. And likewise, a probability abrogation close to 1 yields beta equals to 0, which prevents the spreads of reform from taking place. Now we obtain the following result. In a weighted network exclusively dependent on intralayer connectivity, likely probability of reform completion, regardless of the probability of reform abrogation, is necessary but insufficient to initiate the knock-on effect. And the sufficiency comes from the network topology, where the central nodes ought to be the greatest propagators. We move on now to the simulations with intra and interlayer connectivities. So this time we still have the levels of spillover thresholds. In a multi-layer network with n equal to 100, mu equals to 0.5, different levels of gamma. This time, the x-axis still corresponds to the probability P that node I is reformed by node J. The y-axis denotes the magnitude of inference K n from layer NN. Now, darker blue areas correspond to low levels of spillover threshold, and lighter blue areas corresponds to unreachable levels of spillover threshold, since they approach infinity. Now, with a gradual transition from complementarity to substitutability, we see rising concave curves enclosing a string of bell-shaped areas colored in shades of blue. Now, the threshold increases with K when the probability of reform is close to 0. And as the reform becomes more likely, the spread coming from the layer itself becomes minor, such that the levels of beta vary little. As we go from gamma equal to -1 to gamma equals to 1, going through gamma equals to 0, the spillover threshold goes from a value of beta being simply strictly greater than 0 to a pointless value of approximately 700,000. So when the topology is hubs attracting or neutral, the spillover effect can be easily exceeded, while the hubs repelling topology makes the propagation of the reform unfeasible. The only configuration where the spread could eventually be successful in a hubs repelling topology is would the reform be certain and the influence from other layers be hegemonic. In all other cases, it is frozen.
Just a second. If you wind up in about 5-7 minutes, then that will give us time for at least one or
Yes. I'm accelerating the presentation for you to be able to ask questions.
Yeah.
And this leads us to the following results. In a weighted multiplex network, dependent both of intra and interlayer connectivities, the combination of likely probability of reform completion and of prevailing influence from other layers is necessary but insufficient to initiate the knock-on effect. The sufficiency comes from the network topology, where the central nodes ought to be the greatest propagators. And the final one is about stability. So we have the levels of delta rho that sustain a weighted socio-ecological multiplex systems for delta t equal to 1. So we have a sequence of increasing convex curves with a coordinate equilibrium equal to 0, 0, from which emerge the bell-shaped areas that structures the levels of delta rho. Now, the common origin to all convex curves reflects the fact that the time evolution inside the layer cannot get away from a reform spread initiated on other layers. But it also illustrates the fact that the load between the intra and interlayer conflicts needs to be balanced. And we follow on the following results. In a weighted multiplex network both dependent on intra and intralayer connectivities. The equilibrium density of reform nodes reaches stability with the intralayer interactions be stronger than the interlayer interactions to a limited extent. When the disparity is not more than a certain amount, the socio-ecological system is considered to be synchronized, which ensures stability to its connectivity architecture. Now, because I lack time, I will skip all the discussion and move directly to the conclusion. Now, in a paper from 2011, Dragicevic and colleagues have provided an analysis on the relationship that may exist between resilience and sustainability. Now, based on the idea from Holling, it is spelled out that the ecological economic system in a given state is resilient to exogenous disturbance if it does not flip to another domain of attraction. Other authors have labeled resilience as a dynamic balance instead, which defines it immediately as it is according to the authors. By taking other approaches that those that I just mentioned, our work makes it possible to reconcile sustainability with resilience, stability, and with dynamic balance. And we can say that we have been able to show that the resilience of the socio-ecological system is both necessary and sufficient for sustainability. We have also characterized the stability as a steady state. Thank you for your attention.
Thank you, Professor Arnaud. So we can take questions from the audience.
Yeah, I have a question. Your graph seems hardly susceptible to gamma, right? They're not very sensitive to gamma. So gamma doesn't seem to be a terribly relevant parameter.
No, no, no,
minus
no.
1, 0, plus 1, it all looks the same.
No, no, yes, yes. When you look at the shape of the graph, they seem alike. But when you take a look at the values we obtain, as you move from light areas to black areas, and you move from -1 to 1, you obtain values that are much greater in case of gamma equal to 1. For example, with gamma equals to -1, you need a beta strictly greater than 0. When gamma is equal to 1, you obtain threshold levels that would not initiate the knock-on effect that approach hundreds of thousands. So basically, the values are not the same, but the shape, the behavior with respect to different parameters is the same, whatever the level of gamma. But the threshold levels are not the same at all. But I do agree with you that when you look at the shape of the figures from the simulations, they could look similar.
See, if you actually look at the, I mean, your y-axis is normalized, and with the normalization, it looks practically the same. Even the values look the same.
Yes, yes.
Right? So
yes.
Maybe you shouldn't normalize, just so that at least one graph you should show non-normalized so that we can actually see the difference.
But I think what Professor Arnaud means is that the colors don't mean the same thing in different gammas.
Yes, the shades mean the same. Yes, yes, yes. The shades mean the same.
The colors are the same, right? It's the same color coding.
Exactly. Yes, yes.
Yeah, and that also is the same. So, okay. Anybody else? Anything? Ashwal? Vishal, you have anything to ask?
Okay, so if there are no more questions, we thank Professor Arnaud for his time and presentation, and hope we can have you on campus sometime in the future.
Thank you very much. Once again, thank you for the very interesting comment and question. I'm asking myself whether I should not use other colors to reflect on the differences that we obtain on threshold values. So thank you for that. We like a little bit of distance from this work. So those are the first comments we are receiving. Thank you for your interesting comments. And once again, thank you for the seminar.
Oh, thank you.
Thank you.